In this video, I'd like to continue talking about carboxylic acids, and in particular, we're going to be covering some of the functional derivatives of carboxylic acids, including their nomenclature and physical properties of carboxylic acids and those derivatives. If I were to replace this hydroxyl group on the carboxylic acid with another heteroatom, that would give me one of the functional derivatives of a carboxylic acid. Now you may recall that carboxylic acids have polar bonds. We know that the oxygen is more polar than the carbon, so both of the carbon-oxygen bonds are polarized. We also have a hydrogen atom bonded to an oxygen, and we have two lone pairs of electrons on both of the oxygens. So carboxylic acids are polar molecules. They're also capable of participating in hydrogen bonding with each other. You can see from this figure that carboxylic acids can form dimers with each other, and this makes for very strong interactions. And this will contribute to the high melting points and boiling points of carboxylic acids. Carboxylic acids may also form hydrogen bonds with water, with the oxygens of the carboxylic acids acting as hydrogen bond acceptors, and the proton acting as a hydrogen bond donor. This will contribute to the water solubility of carboxylic acids. If we consider the first carboxylic acid, this is butyric acid. It could also be called butanoic acid. It's soluble in water in all proportions, but as we increase in size, the water solubility is going to decrease. For instance, if we look at the next acid, that is pentanoic acid, it's only partially soluble in water, and once we get to hexanoic acid, 6 carbons, this acid is insoluble in water. So as we increase in the number of carbons, we decrease the water solubility. Carboxylic acids can form extensive networks of hydrogen bonds with each other, and this is going to affect their melting points and their boiling points. For instance, if we compare propanoic acid or propionic acid with 1-butanol, we see that their molecular weights are identical, but the boiling point of propionic acid is 141 compared to the boiling point of butanol of 117. So there's quite a big difference, with propionic acid having the higher boiling point of the two because of the more extensive hydrogen bonding. You may remember that alcohols may also form hydrogen bonds with each other, but they can't form the same sort of networks or dimers that carboxylic acids can form. Let's see if you can arrange the following compounds in the order of increasing boiling point. Go ahead and pause and I'll wait and see what you come up with. Well, the first thing we have to think about is what are the functional groups on these compounds. So the first one, we have a carboxylic acid, an aldehyde, and an alcohol. Both the carboxylic acid and the alcohol are capable of hydrogen bonding with each other. The aldehyde is not. So the aldehyde is going to have the lowest boiling point. The carboxylic acid is capable of forming dimers with each other, or more extensive hydrogen bonds, than the alcohol. So our order is going to be the carboxylic acid first, or having the highest boiling point, followed by the alcohol, 1-pentanol. Finally, pentanal will have the lowest boiling point. As I said earlier, if you replace the hydroxyl group of the carboxylic acid with some heteroatom, that's going to give you functional derivatives of carboxylic acids. These include acid chlorides, so I've replaced the hydroxyl group with a halogen, anhydrides, esters, I've replaced the hydroxyl group with an alkoxy group, and amides, I've replaced the hydroxyl group with an amine. In Chem 2200, we're not going to be talking about anhydrides, but we will be talking about the other three. Let's talk about nomenclature first, and let's look at acid chlorides. These derivatives are named by replacing the ic acid from the name of the carboxylic acid with il, followed by the name of the halogen. So our first example, this compound is derived from a 2-carbon acid. That would be acetic acid. So I'm going to replace the ic acid with il chloride. So the name of this compound is acetyl chloride. Our next compound is derived from a substituted benzoic acid. And the name of the benzoic acid would be 4-nitro or para-nitrobenzoic acid. So I'm going to call this acid chloride 4-nitrobenzoyl chloride. Esters are also derivatives of carboxylic acid, and you may recall that these are made from the carboxylic acid and an alcohol. So we're going to name the ester from the carboxylic acid and the alcohol that it's made up of. So the alcohol group is ethyl alcohol, and the name of the acid is acetic acid. So the name of this ester is ethyl acetate. Ethyl for ethyl alcohol, and acetate for acetic acid. And you'll note that I take off the ic acid and I replace that with the suffix ate, or ate. Think about this example. Go ahead and pause for a minute and see if you can name this molecule. So the name of my alcohol group is isopropyl alcohol. The name of my carboxylic acid is benzoic acid. So the name of my ester is going to be isopropyl benzoate. How do we name amides? We're going to drop the suffix of the acid and add the word amide. So for instance, in our first example, we have the derivative of the 2-carbon acid. So the name of the acid is acetic acid. I'm going to remove the ic acid and I'm going to replace that with amide. So this name would be acetamide. Our next amide is derived from 2-methyl propionic acid. So I'm going to remove the ic acid and replace that with the suffix amide. So this is 2-methyl propanamide. Finally, our third example is a derivative of benzoic acid. So the name of this compound is benzamide. You've also seen that you can have amides that are substituted with alkyl groups on the nitrogen. So if you see that, you're going to also have to name the nitrogen substituent. For instance, my first example is a derivative of formic acid. I have 2 methyl groups on the nitrogen. In order to tell you where the methyl groups are, I'm going to call this NN-dimethyl formamide. Formamide, because it's a derivative of formic acid. NN-dimethyl is meant to tell you that the 2 methyl groups are on the nitrogen. What do you think the next compound should be called? Go ahead and pause, and I'll wait. This amide is derived from butyric acid. We could also call that butanoic acid. And the substituent on the nitrogen is a phenyl group. So I'm going to call this N-phenylbutanamide. I could also call it N-phenylbutyramide. See if you can name these compounds. Go ahead and pause. I'll wait. So these are both esters, and our first ester is derived from 3-methyl-butanoic acid. The alcohol portion is methanol, so I'm going to call this methyl for the methyl alcohol, 3-methyl-butanoate. Our second acid is a derivative of formic acid, so it's going to be a formate, and the alcohol portion is sec-butyl alcohol. So I'm going to call this sec-butyl formate. See if you can name these amides. Our first amide is derived from acetic acid, so it's going to be an acetamide. I have a substituent on the nitrogen. It's a methyl group, so I'm going to call this N-methyl-acetamide. Our second amide is a derivative of 3-methyl-butanoic acid. I have no substituents on the nitrogen, so I'm just going to call this 3-methyl-butanamide. I could also call it 3-methyl-butyramide. Let's talk a little bit about the physical properties of esters and amides. Esters, like acids, have polar bonds, so they're polar molecules. While esters are capable of acting as hydrogen bond acceptors, for the most part they're insoluble in water. They're soluble in polar organic solvents, polar organic solvents like diethyl ether and acetone. Let's have a look at these two esters. My first ester is a derivative of formic acid, the alcohol portion from ethanol or ethyl alcohol, so the name of this is going to be ethyl formate. Ethyl formate is only somewhat soluble in water, and that's a pretty small carboxylic acid derivative. If you get any bigger than that, for instance, if I replace the hydrogen on ethyl formate and I make ethyl acetate is completely insoluble in water. Any ester that's larger than ethyl formate, and most of them will be larger than ethyl formate, is going to be insoluble in water. Amides are also polar molecules. They're capable of hydrogen bonding with each other, and they're capable of forming networks of hydrogen bonds with each other, and dimers, just like the carboxylic acids were. Let's have a look at a couple of small amides. Our first amide is a derivative of formic acid, so this molecule is called formamide. Formamide, pretty small molecule, and it's infinitely soluble in water in all proportions. If I replace the hydrogen of formamide with a methyl group and make acetamide, acetamide is soluble in water, but not infinitely soluble in water. It has a solubility limit of 2 grams per mil. As the amides get larger in size, their water solubility is also going to decrease, just like we saw with the esters and the carboxylic acids. The extensive hydrogen bonding in amides affects their melting and their boiling points. You can see that acetamide has a pretty high boiling point, 221 degrees, and a relatively high melting point of 82 degrees. However, if I substitute one of the hydrogens on the nitrogen and I make methyl acetamide, I'm going to reduce the amount of hydrogen bonding that the molecule is capable of forming. So that reduces both the melting point and the boiling point. Melting point goes down by around 60 degrees, and the boiling point goes down by around 20 degrees. If I replace both of those hydrogens on the nitrogen and I make NN-dimethylacetamide, my melting point and my boiling point go down even more, because NN-dimethylacetamide is not capable of hydrogen bonding. Amides also tend to have significantly higher melting points and boiling points when compared to esters, and this is because esters are not capable of forming hydrogen bonds.